All right. I think we're ready. Looks like one person logged in so far, but that's okay. Oh, well, I will mention last time, the last, I don't know, 10, 15 minutes, when I was talking about, well, I was talking about PID tuning, but the sound wasn't working. So um, I went back and made a short video just on PID tuning with audio. So you'll see another video. I think I don't remember what I named it. Um, PID tuning 2B or something, 3B, I don't know what number it was, but it's just about the PID tuning because there was no audio with the other one. So if you were interested in PID tuning, but you couldn't understand what I was saying because you couldn't hear it, then there is that one video that's, I don't know, 10 or 15 minutes of just PID tuning. Today what we're going to do is we're going to do a little bit more tuning ideas. We're going to talk about STL files, like what they actually are. And then hopefully we get into some common troubleshooting issues that, failure modes that you can address. And so let's start with, I don't see any questions in the chat there, so let's start with some of these other tunings. So last tuning we did was the PID tuning, so that's, if you didn't watch that or couldn't hear it, then what that is that's a better control system for the temperature set point of your hot end, so the nozzle that heats up and melts the filament. It's a better way to control that temperature. So you set a value that you want to print at, and a good PID tune will try to maintain that value as you're printing. Your printer is already tuned in some way for PID tuning. It just may be that the exact location of your printer with your filament and your setup could be a little bit better if you went and redid the PID tuning for your setup versus wherever it was just the default PID tuning. And so there's a video on how to do that. I think first what we're going to do is we're going to do a flow calibration. So let's go over to Cura. Let's see, Cura should be over here. There it is. And let's check and see if I have a flow calibration flow test right here. Let's see what that one is. That's not the one I want to do. Alright, so we're going to make our own flow calibration. So what this is, last time we did go through how to calculate or set the E steps, the extruder steps. So I've done that on this printer, and we should have, if I ask the feeder mechanism to spit out 100 millimeters of filament, I should get about 100 millimeters of filament out. Now that's just coming out of the feeder. It's not necessarily coming out of the nozzle. The nozzle has to melt the temperature or melt the filament and reduce it down to whatever size nozzle you're dealing with. Ours is a 0.4 millimeter nozzle on this printer right now. So there's a lot of other things that are going to happen as between the feeder and the extrusion. So what I want to do now is, well, I know that this printer has a 0.4 millimeter nozzle. So that means that out of that nozzle should come a little strand of filament that's 0.4 millimeters thick. So I want to measure that. So what I'm going to do is I am going to add a cube. Just remember this part for calibration, unless you have gone to the marketplace over here and add, well, let's look at that real quick. Plug in, search for calibration, and then calibration shapes. Unless you've added that, you may not have that particular menu, but I think you can still add parts somewhere in here, but that's the way I always do it. Add a cube, and now I've got a little cube, and we're going to do two things here. One, I don't want to print an actual cube. I want to print just the walls of the cube. So I'm going to go over here in my profile, and I'm going to say that I am at, I want to print what's called vase mode, although Cura calls it spiralize outer contours. So I'm going to search for spiral. So special modes, spiralize outer contours. What that'll do is it will only print the outer perimeters of your model. So not all models will actually print this way because they might have shapes that aren't printable that with only the outer walls. And it will spiralize it, so it will not just print a layer at a time, it'll print like a helix, right? So I'm going to turn that mode on, and just to see what that happens, I'm going to slice and preview. And now you see I've only got the wall. I've got one wall for our cube. Got a couple of bottom layers depending on how many I set, and that's all. And I've got the skirt. So that little blue line, the cyan colored line, that's the skirt. All right, so let's see. I'm currently at a 0.3 layer height. 0.2 is what I would normally use if I were trying to get a kind of nicer print. 0.3 is a faster print, and I'm more interested in speed right now. And I personally do print at 0.3 millimeter layer heights often. So I'm actually going to leave it at 0.3. It doesn't matter what wall count I have here because I have on the vase mode, which only is going to do one wall. It has 3 bottom layers. In order to speed this up a little bit, let's just do 2 bottom layers. Whoop, not 23. Good grief. And infill doesn't matter because vase mode is hollow. Top doesn't matter because vase mode doesn't have a top on it. I'm going to print at 205. Build plate at 50 is fine. Print speed 60 is okay. That's reasonable speed. Part cooling 100%. I am printing PLA, so I do want the part 100% cooled. I'm going to keep the skirt because I use that to kind of make sure that everything's going to print and it stick to the bed well enough. So I'm going to leave that on. Let's slice. And 10 minutes looks still like what I want. That looks fine to me. Let's put our SD card in. You could hear it doing that, a little ding. And it should. There we go, save to removable. We're going to save. And then we're going to eject. Make sure you eject these little SD cards. They're really bad about getting corrupted. This was called Untitled. So we'll go to the printer and search for our Untitled file. So I've already preheated on the printer. Putting the SD card in, and I'm going to print Untitled, and it's going to actually have to cool the bed because the bed was at 60 degrees, so my slicer said it was going to 50, so it's actually going to be too hot for a little bit, and it thinks it needs to cool down. And we'll come back to that in 10 or 15 minutes. So what it's doing is hopefully it's going to print a let's go back to Cura. Hopefully it will print a hollow box. And I should make sure that the line size on this wall is 0.4 millimeters. So let's look for wall line width here, 0.4. Okay, so I hadn't changed that because it's possible that you have a 0.4 millimeter nozzle, but you actually are printing at 0.45 millimeter wall thickness or something. So I'm asking it to print 0.4 millimeter thick walls or lines is what it's saying here, and then specifically wall line width of 0.4 millimeters. So I'm going to let it print, and I'm going to it started over here, so I'm going to make sure that it actually is going to survive the print. Right now I don't have any filament coming out. All right, here's some troubleshooting right now because we don't have any filament coming out of our printer. It didn't do the purge line over here. It didn't do any of the skirt. So I'm going to stop the print. Confirm that. It's going to go through an auto home deal, and we're going to try to see why is there no filament. There's a couple of reasons. One thing, sometimes your filament has broken. You know, if you leave your filament in your printer for an extended amount of time, it can get brittle and just snap over here somewhere, and you don't have any filament feeding. That doesn't seem to be the case. I do have filament in. sometimes your nozzle is just too close to the bed. So it's like the nozzle is smashed down onto the bed where there's no room for filament to come out. That's probably what's going on here. But what I'm going to do is I'm going to manually force filament in. This one has a knob back here. Sometimes you have to release the pressure on the filament and just force it in, like pushing it in, but this one does have a knob. You can print these knobs also on Thingiverse and just add them to your printer. So I'm going to try and force some filament out. And that's not working, so I'm going to... Oh, you know what? It might be cool. It is. It's cooling down. I need to preheat again. So when I stopped the print, it had automatically started shutting down all the heaters, and so the hot end was down at 120. For PLA, it needs to really be at least 175 or higher, and normally I'm printing at 205, so it was below the temperature that it can actually extrude anything. So I need to let it heat back up before we can force filament out of there. Sometimes it's just a matter that it was clogged for whatever reason, and we can just force that filament. Or sometimes it'll retract filament, depending on what the last thing you did was, and maybe the filament just hasn't reached the nozzle yet. So we're going to manually make sure that we can purge the filament out, and then we'll restart the print. I suspect the actual problem is the nozzle was too close to the bed and there was no room for the filament to come out. Alright, so let's see if we can get filament to extrude now. Oh, here's our problem. Look, it was broken right at the feeder. So that is why we don't have any filament coming out. And so that's what I mean, is that sometimes this part that's exposed to the elements can get brittle and break on you. So to fix this, it's kind of hard because it's broken right in here. So I'm going to take this off, unscrew it, so that I can pull the filament out and start over. So there's the broken piece. I'm just going to pull the whole thing out and reload filament. So I planned on doing troubleshooting at the end, but we needed to do some right now. Now, this feeder is super hard to get filament loaded into, so it's going to be one of the first things that we change out. In fact, I've already got an alternate feeder sitting over here that I think we're going to replace this guy because it's just a pain. There it goes. All right. All right, now I've got a little blob of filament coming out. All right, so let's try our print again. Print untitled. All right, so once it starts up again, I'll check to make sure that it's actually printing. It shouldn't take too long. It's already heated up, and it just needs the bed to be actually cooler. I probably should go ahead to Incura now that we're right here and noticing this issue. Let's go ahead and change our bed temperature to 60 degrees. Since the preheat on my printer is set at 60, I could change the preheat on the printer to 50 to match. I need them to match, basically, so I don't have to waste time on either one heating or cooling when I do the preheat. All right, now we've got, oh, you can't see it. Now we've got a purge line, so that's looking a lot better. The purge line is raised a little bit. It's not squished completely flat, so that means the nozzle is at a good height. I'm looking at the skirt now. There's the skirt. The skirt is adhered, so it's not moving around, so it's close enough, and it's raised up a little bit, meaning that it's not squished completely flat on the bed. If it's squished completely flat on the bed, it will stick, but you're going to have that elephant's foot at the bottom. Now this part, it won't really matter because we're not measuring the bottom anyway, but you do want a little bit, like I'm rubbing my finger across there, you want to be able to feel a hump of filament, and you don't want the filament to come loose. So that looks like a pretty good stick, but not being so squished that it's going to create elephant's foot or removal problems. All right, so we'll let that do its thing, and let's go back, and I'm going to show you a website. Let's see if I can find it myself, where you can walk through the a set of calibration. So we've already done some of these calibrations, but this is, let's see, make sure it shows. Yeah, it's at the very top of the screen. So Teaching Tech YT, YouTube, GitHub page, IO, calibration, all this. This is Teaching Tech. I can't remember the guy's name, but he's on YouTube, and he's in Australia, I believe. But he put together a GitHub page that it basically walks you through all of the tunings for an FDM printer in a logical order, and it will generate the code that you need to actually do the test that you're trying to do. So we could have done, here's a flow test right here, we could have done a flow test using his process here. Sometimes he has you load a model into Cura and then slice it, and other times he just generates the G code for you. Basically, this is what the Cura thing that we just made. Now he's added a brim just for adhesion purposes. I don't normally like brims unless I need them, and I don't think I need them for this part. It looks like it's doing fine. So you can kind of see here, frame check, we did that. We did, well, I told you to do that. We didn't actually do that, but you should go through and make sure there's nothing loose, that all the moving parts are secure and not rattling. Your belts are a decent tension, but not over tight and not floppy. Basically, that the hardware itself is in good shape. So we did that. We did our PID auto tune, although you couldn't hear it the first time. I redid it. You can hear it on the second video. We actually, before we did PID, we actually did E-steps calibration. That was where we asked it to spit out 100 millimeters. We measured what it spit out and then adjusted the E-steps. We didn't really do a first layer, but we did level the bed. That's kind of in the frame check thing. I did a baseline print. I don't know where it's at right now, but basically just something at that point to print out that you can compare to after you make other changes. I did print our first little benchy boat for this printer. It was decent. It does have a couple of little strings inside the cabin, and the bottom was too close, and a couple other little bits here and there, but it's actually really good. And now we're on this flow calibration. We're doing the flow test that we devised over here. It's basically the same thing that he does. And then, well, the next thing he says is stepper motor driver current. So what that is all the motors on your printer are stepper motors, which means they move in discrete steps or partial steps, and they have a holding torque basically, and that means that they can hold their position with some amount of torque, so that if it needs to, if something tries to bump it or move it, then it's holding it. And they have a speed, how fast can they get to these different places. And those are kind of related to how much current, electrical current, are these motors drawing. You can modify it on some printers. I actually I haven't looked at this board to see if it's adjustable or not. I do not recommend changing the motor driver current until you're well into the process. Most of them are fine. I have noticed that well, these are fine. So if you start printing and you touch one of the stepper motors and it's blazing hot, then you may need to adjust something. It's under too much load. They should be warm, but not like blazing hot. If you touch any of your stepper motors and they're that hot, then you've got something's in a bind. Your driver current's too high. You're trying to push the printer too fast. Something is wrong if they're blazing hot. Either that, or you are intentionally trying to drive the printer at a super high speed, and you know what your risk you're taking. I don't recommend doing the driver current until you really know what you're doing. Temperature tuning. I mentioned printing out a temperature tower. And I showed you the one that I had printed. It looked generally good at all the levels of temperature, and so I decided to print at 205. Retraction, that's the next one we're going to do. And what's going on with retraction? So let's look at this. So this is the benchy that I printed off of this printer, and I don't know how easy it's going to be to focus on this thing. Let's see if I can get it kind of in the field of focus, and then alright, so you see those little wispy strings and maybe that big one that's sticking out right there. Those are from the nozzle wants to print over here, move into an empty space and print again, and while it's moving in that empty space, get a close-up of our print. While it's moving into that empty space, the filament that is in the nozzle is sort of liquefied. It's very gooey, and it will string across those empty spaces. And so you can reduce those stringing things with a couple of ways. Making sure your part cooling is on for PLA. Other materials, you have to be careful with part cooling because they may not like it. They may get really brittle or they don't adhere to themselves very well if you cool them too fast, or they warp or whatever. But another thing that you can do that doesn't have to do with cooling is retraction. So we need to talk about what retraction means. And I brought up here we go. So I found this on the internet at researchgate.net. You can go see it for it yourself if you want to. It's just a part of a paper somewhere. But here's our spool of filament. Here's our feeder. Now ours does not drive with both wheels, but that's fine. Now in this one, it looks like it's feeding directly into the nozzle. This is a very simplified version of the print setup for an FDM printer. And there are some printers where the feeder is sitting right on top of the hot end. That's not the kind of printer that we're dealing with right here, but they're called direct drive printers. What we have is called a Bowden tube printer, where you've got this tube. Well, we're too close. This tube right here that is kind of constraining the filament. It's being fed over here and then gets into the extruder through that tube. So this picture is not showing the Bowden tube. That's not the point. It is related though to retraction. So what happens in retraction is you're printing your part. You need to move the print head to a new part somewhere, and there's an open gap between those. If you don't retract the right amount or the right speed, then you'll get those little strings between here and the new part you're going to print. In that open space, you'll get those strings. Now the little wispy strings, I probably wouldn't even worry with those. What I would do is take a hair dryer, blow some hot air on those wispy strings, and they'll just kind of shrink back up into the part, and you won't even know they're there. If there are kind of minimal of the bigger strings coming off of there, you can just clip them off. But if you got a whole bunch of stringing everywhere, then it gets cumbersome to try and remove it all, and you're better off trying to adjust your retraction settings. So what retraction does is during that move over the open space, the filament gets pulled back up, so it's retracted. So you retract a certain amount of filament at a certain speed, and then when the print head gets back onto the part where it wants to print again, you unretract. So that means you redeliver the filament to the nozzle and start printing again. So if you don't retract enough, you get stringing. If you retract too much, you get gaps in the new part of the model, like it couldn't feed filament enough to make up for all that you retracted. Sometimes you'll get, if you're retracting too much and too fast, you put a lot of extra wear on your feeder. Maybe it grinds the filament trying to suck it up so fast, because normally the feeders are delivering filament pretty slowly, but the retraction speeds can be kind of fast and maybe they can't handle it that well. So in Cura, you have some retraction settings. I'm just typing in retraction. I just noticed our flow is finished. And here they are. So we'll come back to our retraction settings once we look at our flow test. So there's our little cube, one wall, spiraled, printed. There's our skirt. I just use that kind of as a marker to make sure the part is going to be where I want it to be, and that I've got a good flow of filament coming out. So it's also kind of like another little purge line. This one's the real purge line over here. But it's also just another purge, and it gives me a little bit of time if I need to make any adjustments to the bed level or Z offset, you know, how far the nozzle is from the beds, any of those things. It gives me a little bit of time to do that. So let's pull this off. And that's how they should come off too. If you've got them really squished down in there, then you're going to have to get the scraper out and pry them off. Speaking of that, that's a troubleshooting issue that sometimes it does affect people. They just can't get the part to stick, and you end up having to really squish it on the bed, and then you can't get it off. So if that happens, what you do is instead of breaking or scratching up your surface, take your surface off, assuming your surface is removable. So most of them are. They either are magnetic or they have little clips or whatever. Let that surface cool a little bit, and then put it in the freezer, like the cold part of your freezer, for 5 or 10 minutes, and the part should pop off then. So because you get differential cooling between the part and the plate, and it'll pop itself off of there. But it should be that you've got your print nozzle just the right height from here, where you can just peel it off, and it's really easy. There we go. So now what we want to do, look, I'm a little bit close here. There's some elephant's foot. Kind of see how it's flared out at the bottom. There's still some elephant's foot there. I'm trying to put too much filament in that one spot. So let's not worry about that right now, but let's worry about this wall thickness, so flow rate. So these walls should be 0.4 millimeters thick. So let's see, let's go back over to here. Okay, let's turn on our calipers. We'll have to zoom out a little so you can see everything. Zero them, we're in millimeters, and let's just take measurements across here. I'm going to use the sharp point, and I'm only going to measure kind of near the top. So kind of like that. Look at that, 0.47. I'm supposed to have 0.4 millimeters, but that's 0.47. 0.41, so let's redo that one. 0.4, so for some reason, coming around that corner, I get extra filament. 0.49, 47, 46, 43, 44, and 43. So I'm over extruding. Now remember, when I did the initial E-step calibration, it was set to about extrude 95% of what I asked. What I would rather do is I would rather have the E-steps do what I ask them to do, and then adjust any flow calibrations with the flow rate. So I'm going to go over here to the web page. This is just math, but previous flow rate, we were at 100%. Well, let's make sure. All right, so in Cura, where'd you go? There you are. Typed in flow. My flow rate is 100%. So I'm currently 100% flow rate. Now, I was trying to print 0.4 millimeter walls. I averaged, oh, I don't know, I didn't actually average it in my head, but let's see. 4.4, 4.4. So we're currently at averaging 4.4, maybe 4.5. All right, so it looks like we're averaging 0.45. Calculate. So it says my new flow rate should be 88.9%. That's really low to me. Normally, I'm not too afraid of dropping the flow rate some. In fact, he even gives an important note here. Just because you calculate a thing doesn't make it the right answer, particularly in 3D printing, because the flow rate is just one piece of the puzzle. You've got temperature settings, different filaments behave differently, so it does matter. What you see is more important than what you might calculate. So what I'm going to do is I'm not going to drop down to 89%. For one thing, I'd usually try to do 5%, because it just makes more sense to me, but I don't know that I want to drop down to 90% either. I think I'm going to go to 95%, so I do know I'm over extruding, and I'm going to drop down to 95%, and I will print another one, maybe not in the stream because we need to do some other stuff, but the idea here is that you want to make sure that you're not putting too much filament in a certain location where other filament needs to adjoin that. You know, if like a two walls side by side, or a top or a bottom, because it's going to cram together and you get ripples in the surface or bulges on the outside or whatever. And so I don't want too much filament in a single location. I'm going to obscure details or make the print just bad. So I'm going to drop my flow rate over in Cura down to 95%, and I'll print another one of these. I'm just going to do it universally. Now technically I only measured the wall, so I only know about the wall thickness, but I'm going to do them all at 95. I'll leave these initial layers at 100% because I do want those initial layers solid, but I might have to even drop those down. The initial layers look okay, except that I am getting that in elephant's foot now that I think about it. And that could be also because I'm putting too much filament out. So why don't we drop the initial layer flow. We'll leave the bottom layer at 95. We'll leave them at 95. So now we've got 95s across the board. We'll print another one and see how it does. We'll have to reslice it because the flow rate is coming from the slicer at this point. You can, if you get to printing and you're just noticing that it's just under or over extruding, obviously, you can tune the print on your printer's menu screen and adjust the flow rate there, up or down. All right, back to our retraction settings. Retraction tuning. All right, so like we already talked about, he kind of goes through the what is the point of retraction. In his picture here, you can kind of see all these little strings and wisps everywhere. These are, they're a little bit thick. These would probably be cleaned up pretty easily with just a hairdryer. If you have a heat gun, you could use that. You have to be careful though, because PLA, the glass transition temperature for PLA, so when it becomes formable, doesn't necessarily melt, but it becomes softened, is only like 65 degrees Celsius. So it's 150 whatever degrees Fahrenheit. And you can easily deform your models with a heat gun. Even a hairdryer can do that. In fact, there are some models that's specifically the point. There's a hairy lion, for instance, where all of its mane is printed kind of just straight, and you take a hairdryer and soften up the mane and form it into whatever shape you want. I think there's some beholders that way, D&D minis, where all the little eye stalks are printed straight, and then you can arrange them in whatever shape you want. So you can do it on purpose, but if you're not trying to do that, then make sure you don't apply too much heat. All right, so we are going to look at our retraction settings in Cura. We are using Cura. There are other slicers. We're using Cura. And what this little slicer, or well, not slicer, what this tool, teaching text tool, will do is it will build you a model that you can print with a changing retraction settings to see where is a good set of settings. So let's see what our settings are right now. There's two main ones. Let's go back to retraction. First of all, you have to make sure that retraction is enabled. If you are printing flexibles like TPU and the rubbery materials, you probably need to not enable retraction because they don't do well on an Ender 3 style printer with retraction. They don't do super well with retraction on direct drive, but they at least can do that. But we're printing PLA, so we want this on. There's our retraction distance, and there's our retraction speed. Those are the two most important ones. These others are kind of tuning. Once you get those right, these are kind of tuning that. So 5mm for this style printer with the tube, the Bowden tube on it, is on the short end. And you do want the slowest, least amount of retraction that works for your printer, because the higher numbers, higher retraction distance, higher retraction speed, means that your extruder motor or your feeder motor is having to work harder than it normally would, particularly if there's a lot of retractions in a row. So I want the least amount of retraction that works at the lowest speed that works. Retraction speed of 45, that's actually at the upper end of speed for this style printer. But that's what our current numbers are, 5 and 45. Okay? Those are millimeters and millimeters per second. So we are printing a 0.4mm nozzle. I normally do print 0.3mm. Do they not have? Oh, it has 0.28. That's fine. Let's do that. 0.28mm layer height. I've got some options here. So this option, do I want to include some additional G code to start the printer? I do not, but there are some times where you have a special setup where you've got to change the Z offset of your extruder nozzle from the bed in G code or something like that. You probably don't have this unless you've dug into your printer and written some special routines. Do I have to turn the power supply on? No, I just turn the switch and it turns on. Do I have to am I using a multi-material unit? So I know I'm not. I have one single thread of filament going into my printer. I do not have automatic bed leveling, so I don't have any probes or anything like that, so I'm just going to leave that off. My bed dimensions, I'm going to do 225 by 225 for the X and Y dimensions of the Ender 3. X and Y offsets can be 0, 0, 0. So the origin of my coordinate system at the center, no, unless I'm using a Delta printer, which we haven't even talked about yet. So I'm going to uncheck that. All of these settings, if you're running an Ender 3 or a printer similar to an Ender 3, are going to be the same as these. Hot end temperature, I am going to do 205 because that's what I like to print at. We'll do the 60 for the bed. Part cooling at 100%, starting on layer 2. That's what Cura is doing anyway for PLA. And here are the things that I can test out. So Z-hop means that as I move from one, it's going to print these two columns, right? As I move from one column to the other in that open space, it actually hops the nozzle up, moves over, and then drops it back down. I'm not going to do that. That's useful in some cases, for particularly on the top layer, but I'm going to leave it at 0. Unretract speed, so how fast do I get the filament back to the printer? I'm just going to make those the same as whatever I took it away from the printer. Extra restart distance. If you're retracting and then you're noticing that when it gets to printing the new thing, it's going across the gap and it's printing again, and it's not able to deliver enough filament, there's little gaps everywhere, you might have to add some filament to the retracted amount. So you retracted 6mm, you're going to unretract 6.2mm, for instance. But I'm going to leave that at 0. I'm only going to change these columns here. So I'm going to start with what I already have, 5 and 45. And then I'm going to work on the distance only. I'm going to set all of these to 45. It is tough when you, I mean, I have 6 levels to this thing, but it's tough when you're changing 2 variables at once. So I'm going to go in 0.5 millimeter increments. So 5.5, 6, so that was already 6, 6.5, 7, and 7.5. Once you get 8 and beyond, that's probably too much, unless that tube, that Bowden tube, is just really long on your printer for some reason. So I'm really just changing the length of the retraction amount. And 7.5 is really more than I want to do. But I did notice on my little benchy, I do have stringing, so I need something more. And I don't think it's extra speed, I think it's extra distance. There's our speed, print speed. That's the same one we're using in Cura. I don't need any stop G code, and I don't need to home all the axis. All right, so it will generate the G code for this file. So I'm going to download the G code. Going to go back and get my SD card from my printer. I don't know what it's doing. I guess it was doing something over there. I am going to put this thing called Retraction G code onto the SD card. I'm going to eject the SD card. And I am going to print the Retraction G code. It doesn't give me an idea on how long it's going to take, but it shouldn't take terribly long to print. It's just 2 little columns that are, well, I have one of them. I had one of them. Here's an old one. So it's going to print this. So it shouldn't take too long to print. On Moodle, well, Canvas, I oftentimes print these little things. Notice that this one is showing, this is an example of really bad retraction, right? Let's go over here and look at it. So, really bad retraction. These, with the 4 spikes, they print really fast, but they are always going to give you some level of retraction issues just because of how thin they are at the top. This one is more realistic, right? You can kind of see it started to have some retraction issues. You can barely even see it. There's a little wisp up there. But basically all of these were reasonable. And that's what I'm more expecting, is something like this. This is more of a torture test. So if you try to print in these, don't think that you're going to get your retraction dialed in perfectly where each one of these 4 spikes is clean. You just want it to get it better. This one, you should be able to get a pretty clean somewhere. Some one of those combination of settings should be pretty clean. Let's see, still heating up the bed over here. And this is a more realistic print to begin with. All right, let's see. So it's almost has the bed print heated up, and then it's got to heat the nozzle. Hopefully it'll finish by the time we. I'm not sure why it is homing right now, because the nozzle temperature is only 40 degrees. I guess the way he wrote his G code, it just goes ahead and homes before the nozzle gets up to speed. I don't know if it's going to print a purge line or not. We'll keep an eye on it and see what happens. Let's see. While that's printing, while that's printing, let's look at this idea of what is an STL file to begin with. So let's go over to Notepad. Oh wait, no, not Notepad. Oh wait, maybe we can do Notepad. We just need a different tab. Not that one. That was the notes for what I want to talk about. Alright, so this code here, this is an STL file. This is one that's written in ASCII, so you can actually read it. Sometimes you'll see the option when you're exporting an STL file of ASCII or binary. This would be the ASCII version. Binary would be just a bunch of numbers, right? So this is what an STL file looks like if you dig into it. And it's got, you can read some of this: vertex, loop, facets. It's got a name up here, solid cube. And you can actually open this file and print it if you wanted to. So what an STL file does. So this is the file type. Remember on the very first lecture we talked about some of the history of 3D printing, and back in the 80s they were developing for the resin-based printers and the laser cured resin, and they had to come up with a file type, and they created this STL file type. STL actually is it's a debate on what the acronym actually stands for. I think originally it stood for stereolithography, so writing with light, which made sense because they were talking about using a laser to create the parts in a vat of resin. Looks like our print started fine, so I'll let it go. The current kind of definition for what STL means, even though it's not what it originally meant, is standard tessellation library. And that's more realistic to what it actually is doing. So what you're doing with an STL file is you're taking some CAD geometry. So something made in SolidWorks or Fusion 360 or whatever, some kind of CAD program, and you can't take that CAD files, if it's SolidWorks, that part file, you can't really take that or Fusion 360's file type, I don't remember what it's called, or CAD key or Onshape. They all have these different proprietary file types. You can't just take all of them. There's too many to decode them all. So what you do is each one of those pieces of software has the ability to export to some more generic file type. You lose all of the history, the color, the texture, the material. You lose all of that, and you just get the geometry. But that's all the printer needs, or the slicer needs for the printer, is just the geometry. And how they describe the geometry is with triangles. So that's the tessellation part in the STL tessellation. So what we're seeing on the screen here is 3 vertices to create a facet. So 3 vertices makes a triangle. You use triangles because 3 points in space can only define one plane, right? You can't have, like if I had a 4th point, I could have some kind of curvature to it or whatever. So each one of these is describing a triangle somewhere in space. And each one of those triangles can be arranged together to create the surface features of whatever my model is. Now, there can be issues with that. Let's see what some of those issues could be. You might occasionally load up a model into Cura and it says something about non-manifold, or it says, it's corrupted or something like that. It can't process what the STL file is telling it. I have linked over on here on the web page. I have linked, where did I put it? Non-manifold STL. So if you go to this non-manifold STL page, this link here takes you to this page. So Sculptio's how to fix non-manifold geometry. This walks through what all of the non-manifold things can mean. I'm going to show you what one of them means, but there's several things it could be. Basically, it means that there's some geometry that you can make in a computer that you can't make in the real world, or you can't make it in the real world very well. So that's what non-manifold is. So let's go back to our file here. So we could load this into Cura. I'm actually going to use a piece of software called Mesh Mixer. It's an older open source piece of software, but it's pretty good. For one thing, it can sometimes repair non-manifold geometry, so sometimes that can work. And let's ignore the one on the screen right now. I already opened that one, but that's not the one we want. Let's import, replace the STL file that we were just looking at. So this is what it made. It makes that all that code that we were looking at makes, and it's got flipped normals over here, so that's an issue. But it makes a cube. Each face of the cube is 2 triangles. And so all of these, now these little red lines here, what that's showing me is that that's actually the back side of these faces. These faces in STL file do not have thickness. They are just a plane with no thickness. And this is actually the back of the plane. So what that means is when this code, I guess I didn't pay attention to that, when this code was written, see this facet normal? That means the normal vector, perpendicular vector to that face. In this case, it's actually pointing inwards, which it shouldn't be doing. It should be pointing outwards so you can actually see it. And so this one technically is going to probably create problems in Cura, although Cura is generally good about figuring out what you meant. So it would probably load okay, but all of these look like they're facing the wrong way. But this is created by the by this code, and there's those facet normals that I was talking about. So let's look at a non-manifold one, although this one could be considered non-manifold. Technically it's manifold, it's just the normals are facing the wrong way. Let's look at one that's definitely not manifold. Here we go. So this one is just totally missing faces. Now this looks like a thing that you could print, but you have to remember that these faces here have no thickness, so they only describe a volume when it's enclosed, like it's watertight. So here you could certainly imagine a part like this, but these walls would have some thickness. Oh, hold up, we're not looking at the right thing. You're looking at the code. Here's the thing I'm looking at. There it is. So these faces here only have a plane, no thickness, and the thickness would have to come by adding more faces, right, to make some kind of a little edge and an inside surface and all that. So this would be non-manifold, and it wouldn't print because it doesn't actually enclose any volume that the slicer can make sense of. You can have other non-manifold types too, where maybe you have 2 faces that share an edge and nothing else. So that could be a problem. It's called well, 3 faces. 2 faces can share an edge. I meant a 3rd face that can share an edge. You can't really have that because it makes kind of like this infinitely small connection between the parts, and it probably won't print. So that web page that I linked to, this one goes through several different types of non-manifold situations. There's a 3rd face sharing that edge there. So that's a little bit about STL files in general. It does not look like our part is going to finish just yet. I'll show you what it's doing, just so we can look at it. But looking at it, let's see if we can get down there to it. I can see stringing. They're really, you can't even see them on the camera. But there are some super thin wisps between these, and that's my 5mm retraction, which I already saw that I had issues inside the cabin of my Benchy at that same setting. So I expect that, and I can see them. Hopefully when it gets to some of the higher amounts of retraction, those wisps go away. I think it's hard to tell right now, but the first layer with 5mm has more wisp than the second layer, or second chunk, with 5.5mm of retraction, although they're still there. So I'm going to let it keep going. And now if it ever gets to a point where it's clean, then I can just stop the print at that point. I don't have to finish the whole thing, because I want the least amount of retraction that I can have. Alright, so we'll let that keep going. let's see, what else did I have planned for today? Oh, other troubleshooting. I don't know if I want to get into any of those just yet. Mainly we're going to stick with the retraction. While that's printing, let's just look at some other filaments. I have some filament samples over here just so you can get an idea of what else is out there as far as filaments go. So let's look at them. They're right down here. These are all samples from MakerBox. I don't know what their current, I think they're Box Mountain now. I don't remember what, they keep changing who's actually delivering them, but at one time they were called MakerBox. And so what they do is you get a little subscription and you get some samples of filament every month to try out. So it's an easy way for me to have a variety of things to print. So let's just look at here. Let's turn it the right way. There we go. So shining blue PLA. Now this one has some little sparkles in it. That sounds fun and all, but look at printing temperatures normal, beds normal, speeds normal, fans normal, but notice the other here. So since this filament and other filaments have these too, have particles embedded in them, it can be tough for a standard 0.4 millimeter nozzle to print those particles because they're kind of big. So this one specifically says 0.5 or larger recommended. What they mean is your nozzle needs to be 0.5 millimeter diameter or larger. I do plan maybe even next week to put a larger nozzle because I like printing with a 0.6 millimeter nozzle in general. Because I typically don't use FDM printing for super fine detail, although I will show you some that I've printed that is really good for a FDM printer, but typically I'm using it more for knocking out some part that I want to make. And we need to start making parts for our Rook 2020 printer build, and so I want to make those faster, and so I'm going to use a bigger nozzle. So don't try or be careful with some of these filaments with embedded particles unless you have changed out your nozzle. Also, a lot of times those embedded particles are abrasive and they will eat up a brass nozzle. So don't just change to a larger nozzle. Sometimes you might need to change to a larger hardened steel nozzle. So I'm not going to print this on this printer just yet because it would probably clog it up. Here is, all right, so this one's PLA. No special thing, but it's high impact. So you can get different blends of PLA. There's not like a universal formula for PLA. PLA is polylactic acid, so it has a base set of molecules, but you can have all sorts of additives into the PLA. Some that make it flexible, some that make it more tough, some that make it have these properties like glitter and all that kind of stuff in it. This one apparently gives it a high impact strength. I have not tested that, but it says it has nanoscale additives that debond from the PLA under impact that help prevent material failure. So they've added some nanoparticles of some type that whenever it gets impacted, they somehow release from the PLA molecules and maybe fill in a crack or something like that, or maybe it's kind of like a non-Newtonian thing. I don't really know. Do be careful. There have not been many studies on nanoparticle release from 3D printing. So it could be that you print something with nanoparticles in it, and now you've got nanoparticles in the air and you're breathing them, and so I don't know. I doubt you would have any adverse effects from printing this amount of filament. But maybe if you had a whole print farm of stuff printing this, then that might be a problem. But there haven't actually been good tests. There are tests being done, but there haven't been good tests that have indicated that the off-gassing, well, not the off-gassing, but the particles released while you're printing, even from regular filament, not even stuff that has nanoparticles in it. None of the tests have really indicated that that's a problem until you get into a enclosed space with a lot of printers printing continuously. So in an open space with a printer printing, it doesn't seem to be a health issue until you get into tight spaces with lots of printers going constantly. All right. HTPET. All right, so this is not PLA. This one would not print on your standard Ender 3 for a couple of reasons. So it wants a bed temperature of 270 degrees. There are not many printers out there that the bed temperature can get to 270 degrees. Commercial printers have trouble with that. Hot end temperature 270 degrees. Now you can get your hot end temperatures to 270 relatively easy, but not on a Bowden tube printer. So that tube, well, not on a printer with a hot end where the Bowden tube goes all the way down to the nozzle. That can't happen. The tube itself is made of nylon, and nylon, or not nylon, it's Teflon. And Teflon breaks down, or begins to break down at around 250 Celsius. And so if it's getting heated to 270 Celsius, that's going to be a problem. They do make printers with all metal hot ends that the tube stops short of where the heat is, and that's okay. But you still couldn't get the bed up this high. There's no way that an Ender is going to get their bed that high without serious modifications. So we'll throw that one to the side. Here's some PLA. Just says it prints hotter. Oh, and it has some sparkle. So this one has sparkle that's smaller. So more like a micro, what's that called? I can't think of what it's, mica probably is what's in this. So it's smaller. 220, that is hotter than normal PLA prints, and it does say that it prints 10 degrees hotter. Speeds are normal, cooling, yes, bed's normal. We could probably, maybe we'll try printing one of these, one of our vases in this material. So far, that's our best interesting candidate. This one, so this is a PLA TPU blend. So TPU is a rubber material, so it's flexible, but it's blended with PLA. So somehow this is, I don't know, I've never printed that. That might be an interesting one to print. It says 210, we can get to that. Bed temperature 60 to 70, we can get to that. Doesn't say anything about cooling. So we'll have to figure that out. Semi-flexible. Let's see how flexible this stuff is. It has a cool texture or finish to it. Kind of a semi-gloss. I don't know. Maybe we'll try printing that for our vase next time. See what happens. Because that's interesting. So let's set that one on the side. Armadillo steel color. 220. Really slow. Use glue stick for bed adhesion. I don't know what material it is though. It says it's higher abrasion resistant than nylon. 86 times greater toughness than ABS. I don't know what they're talking about there. Doesn't warp. It's a Ninja Tech product. Normally they make like the flexibles, but that's interesting. Maybe we'll come back to that one. Here's some PETG. I like PETG in general. This one's recycled. PETG doesn't smell bad when it prints. Sometimes PLA does, definitely ABS does. It has some better properties. It's more heat resistant. It's easy enough to print on an Ender 3. Sometimes it's kind of stringy. But I do like PETG. This one's made from scrap plastics. The whole thing. Made in the USA. And it prints at a lower temperature than PET normally prints. So 205. Normally I print at 220 or so. It says it can go up to 245. We might also print that. So these are the three I'm interested in for next time. I'll try to print our vase in these and see what comes out. You know, how well does it work? Our retraction test did finish, and we're about out of time anyway, so let's look at our retraction test and see what it's telling us. So let's see if we can get close to it there and zoom in. Now I see you can see strings everywhere too, so I can see them. They do seem to decrease with higher retraction amounts. They're still there at the 7.5. I don't really want to go much above 7.5. Now again, these I can just remove just by touching them, and then I could probably either run a deburring tool along that edge or just hit it with a heat gun, and that would pretty much disappear. So it's not like those are difficult to remove, but you do see on that surface there's kind of a ridge, serrated edge. That's all the retraction that's not happening. So I'll print another one, and instead I'll pick one of the it doesn't seem like retraction distance makes too much difference. They did seem to get better, but I don't want to go too high, so I'm going to print another one by changing retraction speed and see if I can get what's the best result there, and then I'll take a combination of distance and speed and print another third one and see if we can get tuned in to what our best retraction settings are going to be. All right, I think that's probably, we're not going to be able to print another one of those today. We'll run out of time. I'll go ahead and set it up so that we can see what I'm going to do, and then next time we'll come back with the new settings. I'm going to pick 6 as our speed because 5 I definitely had trouble on the benchy, so I'm going to go with 6. 6 did seem to get a little better. I don't really want to go all the way up to 8, which is kind of the maximum for this printer, and I'm going to I'm actually going to drop down a little bit just to make sure. I'm going to go down to 35, 40, whoop, not 10, 40, 45, 50, 55, 60 is getting really fast, so I don't really want to go much higher than that. But I'm going to try these, see if I get any better results, and then we'll kind of take the best of both worlds, try to, and see what we can do to minimize our retraction. It's not bad right now. None of those were serious. They're just the wisps. But I'd like to not even have the wisps if I can. Some of it will also depend on the temperature. Another thing I could do is I could say, well, why don't we just print at 200? But I don't want to change 2 variables in the same print. I want to just focus on one thing. And I kind of like printing at 205 because it gives me good adhesion between the layers, gives me good bed adhesion, and it just seems to work pretty well. But it might be that I need to drop the temperature down for this filament. All right, I will see y'all on Monday. Actually, Monday, it won't be live. I'll have to pre-record it because I have a meeting to go to, but it'll be a pre-done thing. There will be something at our normal time on 9.